Small signal analysis. We now analyze the small signal properties of the circuit shown in figure A, assuming gamma equals 0 for simplicity. We can apply the half circuit concept to calculate the differential gain here, as illustrated in figure. With small differential inputs, the voltage swings at nodes. Figure asymmetric swings in a differential pair with active current mirror. X and Y are vastly different. This is because the diode connected device M3 yields a much lower voltage gain from the input to node X than that from the input to node Y. As a result, the effects of Vx and Vy at node P through R0x and R0P respectively do not cancel each other, and this node cannot necessarily be considered a virtual ground. We compute the gain using two different approaches. In the first approach, we write mod AV equal to GMR0 mod AV equal to GMR out and obtain GM and R out separately. For calculation of GM, consider figure A. The circuit is not quite symmetric, but here you can see the figure A circuit for calculation of GMB, circuit for A with node P grounded. Because the impedance seen at node X is respectively low and the swing at this node small, the current returning from X to P through R01 is negligible, and node P can be viewed as a virtual ground. Figure B. Thus ID1 is equals to mod ID3 is equals to mod ID4 is equals to GM12 Vin by 2, and ID2 is equals to minus GM12 Vin by 2 yielding I out is equals to minus GM12 Vin, and hence mod GM is equal to GM12. Note that by virtue of active current mirror operation, the value is twice the transconductance of the circuit of figure B. Calculation of R out is less straightforward. We may summarize that the output resistance of this circuit is equal to that of the circuit in figure C, namely 2R02 parallel R04. In reality, however, the active mirror operation yields a different value because when a voltage is applied to the output to measure R out, the gate voltage of M4 does not remain constant. Rather than draw the entire equivalent circuit, we observe that for small signals ISS is open. Figure A. Any current flowing into M1 must flow out of M2, and the role of the two transistors can be, here you can see in this figure, A circuit for calculating R out, B substitution for M1 and M2 by a resistor represented by a resistor RXY is equal to R2R01 to figure B. As a consequence, the current drawn from Vx by RVR XY is mirrored by M3 into M4 with unity gain. We can therefore write Ix equal to 2 Vx by 2R012 plus 1 by GM3 parallel to R03 plus Vx by R04, where the Factor 2 accounts for current copying action of M3 and M4 for 2R not 1 2 very much greater than 1 by GM3 parallel to R not 3. We have R out similar to R not 2 parallel R not 4. The overall voltage gain is thus equal. The overall voltage gain is thus equal to mod AV equal to GM R out is equals to GM12 R out R not 2 parallel R not 4, somewhat higher than that of the circuit in figure A. The second approach to calculating the voltage gain of the circuit is illustrated in figure. Providing more insight into the operation, we substitute the input source and M1 and M2 by Thevenin equivalent as illustrated in figure A. For Thevenin voltage calculation, node P is a virtual ground because of symmetry, and a half circuit equivalent yields V equivalent equal to GM12 R not 1 2 Vin. Moreover, the outer resistances are equivalent to 2R not 1 2 from figure B. Here you can see in this figure substitution for the input differential pair by a Thevenin equivalent. Here in this figure you can see A, calculation of the Thevenin equivalent voltage, B, simplified circuit. We note that the current to R equivalent is Ix1 is equals to V out minus GM12 R not 1 2 V in by 2 R not 1 2 plus 1 by GM3 parallel to R not 3. The fraction of this current flows through 1 by GM3 is mirrored into GM4 EM4 with unity gain that is 2 into V out minus GM1 to R not 1 2 V in by 2 R not 1 2 plus 1 by GM3 parallel to R not 3 into R not 3 by R not 3 plus 1 by GM3 is equals to V out by R not 4. Assuming 2 R not 1 2 very much greater than 1 by GM3 4 parallel to R not 3 4, we obtain V out by V in equal to GM1 2 R not 3 4 R not 1 2 by R not 1 2 plus R not 3 4 is equals to GM1 2 R not 1 2 parallel to R not 3 4. The above calculations of the gain have assumed an ideal tail current source. In reality, the output impedance of this source affects the gain, but the error with respect to GM1 to R0 1 2 parallel to R0 3 4 is relatively small. Thank you.